convinced that the way going forward is to actually try to eliminate those plaques, because as we age, they do build. The toxicity of the plaques is the issue, so probably it's better to actually try to reduce the toxicity, but rather than actually trying to remove the plaques. I'm saying that because the last drugs that they actually approved out was to remove the plaques, and this creating pretty serious side effects in the patients, and the people are not happy about that. But so again, that's an issue. But this particular drug is actually approved to work for mild, moderate, and severe Alzheimer. Obviously, it doesn't treat it, but hey, it's trying to handle the symptoms. The reason why it got my attention is the way it works. So there is a certain enzyme, which I'm not going to even try to pronounce this, that disintegrates this acetylcholine. And this is important for the brain because this is actually a neurotransmitter that facilitates communication about neurons by binding to the ligand-gated ion channels and thus preserving the structural fitness of the ion channels. And this is important to me doing mechanics, looking at structure, because that means that that acetylcholine, if it's present there in the brain, is actually trying to keep the ion channels fit, structurally fit to do the work. So what Donepezil does, it binds to this nasty acetyl whatever and reversibly, so therefore it's increasing the amount of acetylcholine available at synapses, allowing the signal to transmit. It was actually proved relatively recently that also reduces the amyloid beta microglial and astrocytic activation and does decrease neuroinflammation. So there is some good news there as well. Okay, so now the blood-brain barrier. That's creating the biggest problem of delivering drugs to the brain. People have tried to say, oh, let's bypass it and let's use ultrasound to increase the permeability. Let's do all sorts of things. All I can say is, maybe not. You want this brain-blood barrier to actually be intact and actually work. And that's one of the main issues here. So what exactly is the issue? At the capillary bed inside the brain, we have this, right? So you see the lumen, right? The capillary lumen, that's where the blood is. You see the endothelium, right? It's just a very thin, very tight endothelium cells. We see the pericytes, some other type of cells. And then, of course, we also have the astrocyte fits there. Very important, since those are the ones that actually communicates and signals, take oxygen, take all sorts of things to the neurons. By the way, they do share, all these cells, they share a basal membrane, and that's important for all the purposes. What it's doing, obviously, is not allowing bad stuff to go into the brain, but also it creates the problem that it doesn't allow drugs to go into the brain, right? So it's a give and take. Another thing that is probably relevant is that those amyloid beta plaques are not only coming from building outside. When Alzheimer starts to build, they have started to show that it could actually come from the blood as well. So as the blood-brain barrier starts to disintegrate during the Alzheimer progression, the plaques are actually everywhere. The mechanism of the crossing, transcytosis, efflux, paracetoral transport, carrier-mediated transport, diffusion, plenty of ways to actually carry drugs across. However, I am going to focus on specifically to transcytosis because of the way it does it. There are some ligands sitting here that are actually absorbing certain particles, molecules. Then they use vesicles to actually take the particles and move them all the way into the brain, and then they are released back using some sort of ligands. And this is actually a very promising way to take nanoparticles across into the brain. So with that, models, right? So obviously mechanism of health and disease, design drug delivery and releasing systems. That's what we can do with the mathematical models. I don't need to say any more of that. I'm preaching to the choir here. The published models of drug delivery, release, and transport to the brain with AD focus actually only on the temporal dynamics and the drug concentrations and ignore specific structural and biophysical aspects of brain and the spatial variations. If we actually really want to do targeted delivery, a spatial distribution of things becomes relevant. So what I'm doing here, I'm proposing a model for Donepezil transport to the brain after oral administration that incorporates anomalous diffusion due to the structural damage and accumulation of harmful waste in the brain caused by the disease and the BBB transcytosis. And this is the model. It's actually pretty simplistic. As you can see, I have the lumen, the capillary lumen here. I have a very small layer of BBB here and the brain outside. It's a cylindrical asymmetric geometry, nothing too complicated. Of course, this is my equation, as you probably recognize it, Fick's law, since we're talking about last night. And I do have all sorts of processes of adding, right? So this is where it's a source term that is actually adding drug to the lumen. Then processes where things get eliminated from the brain and from the lumen. And the most important terms are actually here, is the way it crosses the blood-brain barrier via the transcytosis. So literally, I have to make sure that whatever is coming at this interface is going to be taking the same concentration, right? The same amount is going to be taken into the brain. So by the way, the reason why I have some extra term here has to do with the fact that this is actually a generalization of a pharmacological model that was done last year exactly for this drug. Okay, and H, by the way, is the heaviside function. So you realize that what's happening, the way you differentiate between different regions is using the heaviside. With that, by the way, one more important piece here, the interface. So this interface is here between the lumen, right, and the BBB, and also between the BBB and the brain are not crisp boundaries. In other words, are not exactly where the structure ends. That's where the boundary is. They are fuzzy boundaries, right? Because we have biochemical processes that happen on a bit wider regions, right? You have those ligands reaching out or releasing drugs, right? So that's why I have an extra term there, beta, that was actually accounting for this type of extra thickness, if you want, of the layer. I'm not looking at existence. Existence actually was proven. I'm looking at anomalous diffusion. So fractional derivatives, I promise you that.
So far, anomalous diffusion was not there.
It is here. Let's look at it. Okay, so there you have it. So it is going to be using the Riemann-Liouville fractional derivatives. They are non-local derivatives. So there you have it. These are the generalized Fick's law. By the way, they were actually proposed first to look at porous media and actually how rivers are created. So in case you're wondering what other people do, the advantage of being in engineering departments is that you find out what other people do, and it's fascinating. And these are some initial conditions. Lovely, everything goes back. Shane, what exactly happened? Oh, it's back. Integral differential equations.
And then in this case, you're adding the additional parameter because the fractional derivative.
It doesn't bother me, and we're going to see why that extra parameter doesn't bother me. I know that we like to be careful, but we'll see why it doesn't bother me. Okay, so with that, boundary conditions, obviously I have a source term that I know how to add a drug into, and this is the trick. So I looked at two aspects, right? So you realize I did have to look at the classic case, which you are going to see epsilon equal 1. I do have some skewing going on. In other words, preferential in diffusion directions, right? So if you see PR equal PZ equal to 0.5 is the classic case. Diffusion goes to left and right, to radial and longitudinal, it doesn't care. But the next case, you're going to see a skewness in the direction of the drug. So what I want you to see is here. So this is brain at different values of Z, right? So I'm going inside the capillary and at different values of R, meaning deep into the brain. So the black one that is more relevant is immediately outside the blood-brain barrier, okay? So this is the classic case here. This is actually, I'm actually more interested in. I do get more, as you can see, the peak at various locations are actually higher if I'm actually using the fractional order of this manner. The number is coming actually from a paper where they were trying to actually deliver Donepezil to the brain in certain polymers. And that was one of the experiments that they propose a value for it. So it turns out that in the presence of in the presence of the transcytosis, I am actually getting better results if I'm accounting for anomalous diffusion than the classic case. But what's interesting, what's happening next, if I take away the transcytosis, the first thing is interesting is that the decay in the classic case is very fast. So if you actually go and look a bit, right, so you see the width is bigger here, right? So roughly around 100 minutes, it finally fully decayed, right? But if you take away the transcytosis, the decay is very fast, right? So the width is not there. Not only that, but you see also the maximum concentrations are much lower, right? So it's of order 10 and minus 4 instead of the 10 and minus 3. In this case, so you see, I need more, well, not more. The length of the Levy flight has to be a bit higher, plus I need a skewness in the radial direction in order to actually get higher concentration in the brain and still get some slower decay of the drug. So that's actually one big advantage of doing this. Why I will eliminate the BB transcytosis? I don't want to eliminate it. I'm just pointing out we need it. But the problem is that as AD progresses, the BBB gets disintegrated. And this is actually tremendously wrong, because I dare to hypothesize that when the BBB goes, the patient decay, it's pretty dramatic. There is no blood flow anymore. There is no oxygen to the brain. So in other words, the degeneration, it's speeding up pretty fast. So what exactly we have seen? Both the functional transcytosis and anomalous diffusion are essential for increasing drug concentration. It is not an increase in the drug dosage frequency, but rather different drug delivery and release modalities that depend on the severity of the disease that may increase the treatment. And this is actually a nano pill I was proposing, where the molecules of the drugs have to be inside certain have ligands that will actually physically achieve this, be able to travel to this anomalous diffusion, be able to reach like arms, connect to the ligands in the system, and actually get there, right? Otherwise, just pure diffusion. And by the way, biological tissues do have the ability to do what's called facilitated diffusion, very similar to passive diffusion. So this is not really something totally new. We can make use of it.
The anomalous diffusion usually within the special code. There are the computer dealing with the time. Anomalous diffusion dealing with the spatial code.
This is spatial, yes. This is Levy flight, yes. Yes, yes, yes. But you are correct in the sense that in the second model, I did do time. So this is actually very quickly, because I am running out of time. This is actually the original paper by Kalikosidis. I just changed the, right, it was a compartmental model, right? Classic stomach, blood, brain, and some peripheral. I replace it with a fractional derivative to do subdiffusion. Okay. By the way, the nice part is that I can find an analytic solution, but that's a different story. And then this is what happens. The case that I'm actually interested is in this one. I don't really want a high concentration in the brain. I want enough that slows down, right? So it's the one that's decays the slowest, so that actually I don't have to give another drug too soon, right? To increase the concentration. So that's the case that I'm looking at epsilon equals 0.658. Why I'm interested in that? Because now this is viscoelasticity. So very quickly, that's why I was asking about constitutive equation. This is a constitutive equation. Please note the fact that I have a fractional order that is it's a variable function, trip compliance and relaxation modulus. Why is this relevant? Because the way people look at fractional derivatives is a long tail. This is the long tail. In the relaxation function, right? So the blue, right? That's actually the short tail corresponds to a decaying exponential, right? And then, of course, you have the long tail actually showing up as memory starts to build. In other words, as the fractional order decays to 0. There are some other very nice things that you can do using the HAR piecewise constant approximations, where you can actually investigate using analytical solutions, investigate how the intermediate behavior of a variable order. And this is the catch. The catch is here. By reinterpreting the famous Hutton-Huxley model, where these M and H were gates, I'm now giving them a structure, and I'm giving them a structure of viscoelastic variable order fractional Maxwell materials. I can actually obtain models from the Huxley-Hutton model with damage. So the action potential, the black one is the ideal case, and then as I build memory, viscoelastic memory, the action potentials don't happen anymore, right? So this is a neat piece. And finally, the last piece with my Beer's apology. So what if I actually propose a variable order for my ion, the viscosity of my ion channels that are some delta, where delta means it's a, I don't know, 0.75 when I'm actually damaged, right? My ion channel is damaged, and I'm adding the concentration of the drug that I have. And it turns out that if you remember that glorious 0.658 that I had earlier, I can actually get action potentials pretty good for a long period of time, rather than just the classic epsilon equal to 1 that is not going to do such a good job. Thank you so much. I truly apologize for the extra time.
Okay, thank you very much, Corina. We're going to go to a question from Siv.